So welcome everyone. Today we're going to talk about real-world AI ML use cases and performance modeling, and first offer you a kind of a background where our AI and ML comes from. I'm Muslim Elkotob. This is Dr. Ragana Chaparadza, my colleague, and we're going to kick off right away and be with you for around 40 minutes today. So today we're going to cover, first of all, what are the architectures that support autonomics, automation, autonomics as a built-in procedure in the architectures, and what are the architectures that enable native AI and ML. We're going to cover in this scope things like automation and where the stakeholders that need automation, like operators, like vendors, like integrators, where do we stand today. Then we're going to talk in detail about our partially self-developed ETSI, GANA, which is the generic autonomic network architecture. It's a standard which has multi-layer autonomics. And it's a key enabler for multi-layer AI and ML operation in autonomous networks and beyond. Then we're going to cover test automation with AI and ML, using autonomics to automate testing in complex scenarios. And we're going to talk about also multi-layer framework for AMC, which is autonomic management and control, AI model implementation. So it's about real implementation of models which are AI-based. Founded on the GANA framework. Then we're going to cover a huge array of use cases which are partially in place, partially being still developed and enhanced. The first one is about cognitive security, behavioral modeling, and federated autonomics, meaning that how do you make security behavior, security workflows shaped according to the needs of your customer, of your use case, how do you shape behavior in particular focus on security aspects. That's one use case we're going to talk about. The second one is about AI-based autonomic test systems and the concept of a marketplace, meaning that stakeholders are like on a marketplace. You certify different assets, you trade assets, and you then enable advanced functionality. Then we're going to talk about AI-based certification and role model. You need different roles inside each stakeholder so that you can really interact in the proper way there. Then we're going to talk about federated testbeds and assets. And finally, Telco Data Space. Exactly. And so to kickstart it, what are some architectures? We're going to go into details, and together with Ragada, we're going to really give you a lot of insights there. So starting with architecture supporting autonomics, AI, and ML. What is the background? Where do we stand today? So operators or communication service providers, the likes of our company and other large operators, they're undergoing what we call digital transformation in the architecture itself, down to the core, down to the native functions. Also in their big vertical stacks of OSS, operation support systems, like inventory, monitoring, and also BSS, SAP, billing, etc. And also processes are undergoing transformation, and the service spectrum, what do you offer as services? It's more IT-based, more software-based services, less of, let's say, old-fashioned telco. And in all of this transformation, automation is the key, and it's also reflected in different, let's say, facets. One of them is process automation for network or CSP operations. One is the side of workflows, and not the buzzword, but something which is a challenge even today, orchestration. How do you orchestrate the different elements to enable the behavior you want to achieve in your use cases, which are derived from your business cases? The topic of resource management, especially in end-to-end network slicing with standalone 5G, which you all know standalone 5G is that the core is software-based. You have end-to-end visibility of your resources. You can connect, and then you can run your slices and then provision resources dynamically. And then we're going to talk about also a very important aspect, which is automation frameworks and standardization approaches. Both of us are very active in SDOs like ETSI, ITU, IEEE, 3GP, and GSMA. So that's why we also drive the automation processes, just like GANA is an ETSI standard, for example. We drive the processes that we develop to be parts of standards in our roles also in SDOs. So there we're going to talk about, as I said, ETSI GANA in detail. It's a mature framework for multi-layer autonomics. We also have some aspects like zero-touch operations, which is the motto of some SDOs or vendors, but it's all about minimizing the human interaction, the error, and giving it over to the machines, the AI-driven machines, to really take the decisions in the process and enable, let's say, automatically figure out what behavior you want to really achieve. So this is basically the motto, what we drive here. And now I'm going to dive into this slide together with Raganai. So we mentioned ETSI GANA, generic autonomic network architecture. This is the blueprint or the picture of the GANA architecture. So what do we see here? We see that there are 4 layers, which are actually abstraction levels. So the lowermost layer, you start at the basic level, which is, let's say, your protocol level, So you have basic protocols, which are pretty concrete, not very much abstracted. Then you have over that the function layer. Function is more abstract than the protocol. So you are able to, let's say, have more cognition, more metadata. Then level above it is node level. It could be any entity which could be conceptualized as a node. And then the highest level, which is the brain of the system, it's called knowledge plane. This is one of the core elements of the ETSI GANA design. And in such a multi-layer architecture, if you build, let's say, or map your operator CSP architecture to this one, you will have then every entity mapped to a certain layer. And these layers, as you go up, you get more cognitive, more abstract, you have more information. As you go down, you get more concrete. And the idea here is that we have what we call control loops and closed loop automation. We talk about automation, autonomics as an enabler for AI/ML. So a closed loop is let's say, a closed function circuit that's doing monitoring, observing, and then reporting back, feeding back to the element. So you have control loops at the lowest layer, which is the protocol layer or the function layer. And this closed loop, it gives the entity awareness of what is going around. It's evaluating data from the previous cycle, current cycle, from other contexts, and figuring out what is going on. This is the context-aware, let's say, closed loop cycle. And as you go up, the loop gets bigger because, for example, if knowledge plane covers the whole segment of a RAN or a core of a network, it is a big domain. The loop takes time to close. That's why it's called slow control loop. You can see slow control loops. And the lower, let's say, layers, they have fast control loops because they converge quickly. It's a very quick cycle on a small entity to converge. So with this abstraction layering, conceptualizing, closed loop automation, and this different navigation up and down, you are then able to gather in the knowledge plane awareness about what is in the system on the lower layers, and you collectively evaluate what is being, let's say, fed up in the upstream cycle to really combined information, evaluate it, deduce, and then develop cognition of what is going on in the system. And Raganai will now give you more insights into this as well.
Yeah, thanks, Muslim. I can add something on this. So basically, I think most of you are familiar with the concepts of autonomics, which is really the closed loop concept, which is a control loop concept. And this is the science behind what we call the autonomics, as most of you are familiar. And one thing that is very interesting for us to understand is that a reference model has been developed which enables to design the software that drives control loops. These are called decision elements, as my colleague has just talked about, meaning that the design for the DEs start with the lowest level of abstraction, which is the protocol stacks, what we see at the bottom. Maybe if we can go to the other one. Yeah, exactly here. So at the very bottom, we have protocol stacks. And we can abstract the different protocol stacks by way of saying what sort of autonomic component or software module should drive a control loop with an algorithm, right? So we end up having, let's say, decision elements for quality of service management, for mobility management, as well as for forwarding management in terms of behavior. So the interesting thing is that what you see here as a node or network element, today we have this dilemma where we think, should we push a lot of data into the data lakes and then we keep the network dump? There's a challenge to that. The challenge is that it's very expensive to pump a lot of telemetry data from the network into some kind of data lake there. So what we are saying is that the network itself has to have its own intrinsic intelligence in terms of what sort of monitoring data can be exported and reporting reports to the upper layer, which we call the knowledge plane, that is the global view of the network. So those are the trade-offs that we are looking at, because it's quite expensive to pump a lot of monitoring data out of the infrastructure to some data lake. So we are saying that we have distributed intelligence. We're talking about distributed intelligence, where some intelligence is delegated to the network element itself, the switch, the router itself, right? And then over the top, there is the umbrella platform we call the knowledge plane, which is operating with slow control loops and is receiving reports of certain situations that the network elements are not able to handle on their own, right? So that's the philosophy behind what we call multi-layer autonomics. And what does it mean in terms of AI? If we go up from the network element, going up into the knowledge plane, we see that the complexity of the AI algorithms is then increasing. We are coming from zero AI, let's say at the protocol level. If you look at one particular protocol like TCP or OSPF and you put some intelligence in it, you want fast reaction. You don't need complexity. You don't need a lot of AI. You don't need even AI and such. But as you go up into the knowledge plane, you need more complex AI, more cognition. So the degree of the cognition of the network is increasing up into the knowledge plane, right? So this is the GANA, the reference model that we have worked on in ETSI. What does it give to developers? It gives a guide to developers as to the DEs, how are they positioned? How can they interwork with respect to escalation of situations, for example, right? We don't standardize the algorithms. The algorithms are the IPR, the differentiation from the vendors, right? So the intelligence is coming from innovators like you guys, right? You can innovate the algorithm, but we give the framework, the containers where the algorithm will be running, right? So that's the GANA framework.
Yeah, exactly. And
then zooming in onto this is that we are now looking at the knowledge plane. We have moved into the era we call knowledge plane-driven networking. We are coming from networks. Some of you may be coming from a different angle, but we come from networks, enterprise networks, telecom networks, and the like. So we really look at the segmentation of the network, the red geo, the transport network, the core network, as we said. And we said, in terms of network disaggregation, we are talking about disaggregation. We can talk about disaggregation in the red geo, like you have heard about Open RAN and the like. There's really a traction on disaggregation. It gives its own benefits, but also on the management and orchestration layer, we are calling for disaggregation. So we are looking at a knowledge plane for each particular type of a network segment. For the radio, for the transport, there is a specific type of or specialized knowledge plane. The interfaces between the data sources that feed into a knowledge plane, as you can see here, is the exposure of the northbound interfaces from the different management systems. The OSS, the EMS, the MANO, management and orchestration stack, they push data into the knowledge plane. The knowledge plane has complex event processing and cognitive algorithms, very complex cognitive algorithms, the DEs that are running there. For QoS, for mobility, for different type of areas of management and control, as we call that, the AMC. And so that's how we look at the knowledge plane, how to design, standardize the knowledge plane in terms of the integration with northbound interfaces of various type of data sources. In 3GPP, for the core network, we have the different type of analytics functions that provide services that can then, as services, as analytics functions, they can provide services to a knowledge plane for the core network. And on top of that, we are also looking at a federation between different knowledge planes for the RAN, for transport, and for core network. What is the target? You have heard about self-X, self-configuration, auto-discovery, self-healing, self-diagnosis. This is what we are moving towards with the networks today, right, into the future, right? So so that you can understand what is the paradigm. Next slide. Yeah. Then what we also took a look at as ETSI, as we were looking at the standardization of automation in the intelligence. On the left-hand side, you see different domains. You have domains of the operator who runs OSSs, you have the domains of the vendor who has EMSs and network elements, and we are saying that on each of these levels, there is the control loops or cognition modules that can be developed to build a multi-layer intelligence for the network. In terms of managing the business, we can talk about cognitive business assurance, cognitive service assurance, and then underneath the substrate, which is the network and its associated management architecture, is then the autonomic management and control for the network, right? So, and then on the top, we are moving towards intent-based management, where, you know, the intent expresses what and not the how, right? And it is up to the network to then figure it out how to do it, right? So this is where the operators want to really capitalize on intent-based management. So in other words, the knowledge plane is positioned to be the anchor point for service management, cognitive service management, and cognitive business management. Thanks to the control loops, thanks to the AI that empowers the control loops, the decision elements. So this is the framework that has been standardized in ETSI.
Yeah. And actually intent is the what, as Ragana said, and the how is configured through the cognition. Yeah. Cognition gives you the way, how to get there, how to use the resources, how to really combine everything together. So got this kind of view now. Yeah, here it is just overview how when we apply, let's say, we have different, let's say, discourses where we apply autonomics, multi-layer autonomics to different areas. If you talk about, let's say, testing or in AI, you talk a lot about training, also in machine learning training. There's a set of, let's say, cycles and means how you get there. So when we do, let's say, test automation in different, let's say, use cases, and we apply AI or use AI as a support means for automation, and also, of course, in the autonomics frame, as we just described, we have different, let's say, stages. So there's a stage where there is today a challenge. Every one of them is a challenge day, and there are companies popping up. Yeah, we can do for you this and this. So data collection is the starting point, and aggregation and integration. Data collection is also about, today we have it, we will show in the end of the presentation, about data sharing. When you want to collect data, you don't have access to all of it. Some of it can be shared under certain conditions, or you don't have, let's say, the means to access data which you need for some AI algorithm. So data collection is a challenge technically and also from a process or legal perspective. And there are different, let's say, functionalities under this, let's say, stage. The development of the architecture, the code, then there are the test cases and other different steps, operational data evaluation, basic analytics, etc. In the core or intermediate stage here, or in the middle pillar here, you can see what is, let's say, the core of when you apply AI and ML techniques. What do you have? You have the learning process, so you learn what is in the environment, what is happening, what do events mean, what do they collectively mean, and what to do about them, how do they align with your policy, what should you do to let's say, apply a certain intent if you're dictated some intent by your business customer. The creation of knowledge also, and adjustment of your behavior, because also AI and ML are continuously tuned mechanisms to adapt. You cannot always have, let's say, the sharp bullseye hit with the AI. You keep learning and adjusting and tuning to really match in the best possible way the behavior you want to achieve. And there are some mechanisms that we also use because ETSI GANA is a framework, but inside there are different, let's say, instruments and elements. And basic ones that we use, or which are also commonly used, are rule-based engines. It means that there's an engine, you feed in rule, if this, then this, and this, and this, and then you have, let's say, you have different languages like Prolog even, or others, where you can really evaluate those rules and then create a decision. We have reasoning modules, decision trees as well. Workflow management, there are so many tools around, it's still a challenge, but it has to be something which can flexibly capture all stakeholder requirements and then really, let's say, simulate the workflow you want to really achieve. Deep learning, and also classical monitoring and learning. So you observe and you learn, you keep feeding in what you monitor into your learning algorithm. And then the actions and executions, there are things like predictions. If you talk about security, there are, let's say, weak points you may see there. There is selection and prescription for use cases. So you have, let's say, a huge set of use cases and use case variants. You vary every time a variable or a stakeholder. So how do you really classify them? How do you identify them? What weight do you put on each one? It's also some outcome you want to have from your AI applied to the testing area. Self-optimizing, self-based testing, process automation in general, and of course in detail and in high complexity in the GANA framework, and just regular learning, knowledge creation and processing. Here, Ragana, would you like to?
Yeah, briefly, just to briefly talk about the continuous learning and training of AI models, especially focusing on the decision elements that we talked about. It's multi-layer decision elements. The interworking of the decision elements is a framework that we have worked on in ETSI concerning synchronization of actions and policies at different levels of the abstraction of the decision elements. Then, given that framework, we have also been looking at stability of control loops. Because when we design autonomics, we talk about really interesting intelligence that has to follow certain, let's say, techniques on stability of control loops, right? So there is a science that we have worked on over the years in research globally around the techniques to address stability of control loops. But coming back to the aspect of training, the DEs. So we are distinguishing between the distributed DEs, which is the decision elements that are delegated to operate within the network infrastructure elements, the network functions. And then we have the DEs in the knowledge plane, which is a global view of a scope of a network. So the radio, for example, is a scope, transport network is a scope, or core network is a, or a data center is a scope, right? And so when it comes to that, to the framework on training, we consider this continuous training for the DEs. And then comes the question of how the intelligence of the network will evolve over time. We have come up with an understanding of two perspectives. The first is the improvement of the AI algorithms over time. The network is intrinsically having the DEs embedding AI models. And this, as they improve the DEs in terms of the quality of decision-making in the algorithms, this is how the network becomes more and more autonomous in terms of its operations. And then the other evolutionary aspect of intelligence of the network, of the autonomous network, is through the marketplace, right? So what operators are saying is that they would like to look for best of breed of decision elements. If I want to focus on mobility management, I should be able to source from the marketplace the best of breed of a decision element for mobility management or for quality of service management. And I should be able to onboard and remove and put a better DE as driven from the marketplace for evolution. So there's this framework we have worked on, and for the sake of time, there's a paper that we also have published here, so you'll be able to access, I think they'll be able to access the slides, right? So,
yes,
but you can go
exactly.
ahead.
Slides will be available, and the link, it's public available white paper which details this out. And here we also just want to show you that AI, it starts with, let's say, pilot data, training, and then you finally get to the right mode. Here we have the ability to, let's say, reflect our GANA framework one time in what we call, let's say, a training environment. One time is the real production environment, and then they can also interact and exchange learning information. So that's why it's like this two-stage instantiation to, let's say, reflect the two cycles of AI until you cannot directly throw in algorithms into your live network, for example, as an operator. This is what you get here.
Yeah. And which brings, by the way, if you go back to that previous slide, which brings back another, point we I'll emphasize in the slides, which is about trust and confidence building in autonomous networks. So this enables, because as you build trust, as Muslim said, integrating by these two environments, you can then build trust over time and be able to activate the DEs to be operationally in closed loop in the production network. So, but there will be another slide I'll cover on that.
Yeah, we'll talk on that. Now we're going to talk about cognitive security and federated autonomics. This is the first use case we're going to show you. We're going to both talk about this item. I will start here. So basically, what we did you can see the link here. We did a white paper. We did also a demo in the POC, and we demonstrated actual security behavioral shaping. So what is this about? We had two operator networks, Vodafone and Orange, each one reflected by or mapped to the GANA multi-layer autonomics architecture. And when we have, let's say, as Ragada mentioned, different network tiers like RAN, transport, X-Hall, or core, they can be each governed by its own knowledge plane, or the whole operator could be governed by a knowledge plane. And then you can talk between knowledge planes. Let's say two operators, each has a knowledge plane. They can talk through what we call federation. Federation is a trust. We'll go into details about that. But federation is mainly about a trust relationship and exchange of information and assets which are leased out or traded or shared for a specific, let's say, business purpose. And in this case, the basic thing behind this, and Ragnar will also give you some more insights, but the basic idea is that we had Vodafone and Orange, two networks governed by their own knowledge planes, and there is a user roaming in the Vodafone network, and then he's downloading data, he's downloading some files, he's using some services, and then there is some security threat or some infection detected. So then this information in the security, this is a security behavior demo. The systems that detect security threats, they're passed on upwards to the knowledge plane, which is the cognitive, let's say, engine of that operator. And it's processed to evaluate what kind of threat is this, what is to be done about it, what does the policy say, is it in the database of threats. And then, based on that information, after it's processed and produced in a meaningful and valuable way, it is passed on horizontally at knowledge plane level to the other operator, which is orange, so that when this user or other users are roaming in that network, the orange knowledge plane is informed about this threat, and then it passes on downwards. So it first goes up to the knowledge plane, it's evaluated, it's processed, it's passed on horizontally to the knowledge plane of the other peer operator, and then it's processed down to its entities like the nodes to tell them what to do or to be aware of this threat. So this is what we actually showed together here. It was a demo, quite advanced. We had Checkpoint as a partner here, and Ragana will give you some more.
Yeah, exactly. So the federation is on two levels. One, you federate information. A threat is detected in one domain, then is hashed, and then can be shared. So depending on the SLAs between the operators in terms of federations, you could federate in terms of information sharing. And then you could also federate in terms of what sort of actions could be attached to a particular type of a threat, right? And negotiations between two domains. Let's say when you have, within the same operator, you have a threat detected on the access, which may have impact on the core network. The knowledge plane for the core network may have to learn that kind of attack in order to compose services, dynamically configure the core network to remediate or proactively, let's say, avoid an impact on services from the threat detected in the access network. So federation on level of information, right, like security threats and the like, predicted or detected, or federation in terms of also decisions that have been exercised practically to remediate a problem. It can be shared to Orange from Vodafone knowledge plane, for example.
Yeah, exactly. Keep going, we have many use cases
to cover. Then on this part, well, the other aspect, because like we said, we are walking you through use cases of AI from the operator's point of view, but also vendor domain. One aspect that we want to highlight here is that comes the area of testing. We as CSPs, we have very complex legacy networks, and they are growing, the networks. We are bringing new technologies on top of old technologies. The question of testing is quite interesting from the point of view of complexity of the networks that we want to test, but also the emergence of AI. How do we test AI embedding systems? And what would be, let's say, verdicts that can be used in test cases to test the AI, right? So this is a subject that we are addressing in ETSI on AI in test systems and benefits of AI in test systems. One of the concepts that emerged from there is a concept called autonomic test system. The autonomic test system is an intelligent test system that in itself also is employing AI to address the complexity of testing a very complex network, for example. What is that intelligence doing? The intelligence is able to select what sort of test cases can be executed based on the intelligence of the test system and its prediction of the state of the system under test or network under test. So there is an intelligence that can be embedded in the test system. So we have come up with an architecture of so-called autonomic test system, and there is a specification that you see on top there, an ETSI TR, which describes the concept of an autonomic test system. And what is the value of the autonomic test system in terms of test services orchestration, test suites and test cases definitions, as well as those kind of at the bottom you see the system under test, the network under test, exposing different type of, let's say, internal probing data as well as monitoring data, and the test system is able to drive the SUT into certain states. And intelligently, as an autonomic test system, it can then become a qualified test system in the sense that it qualifies towards certification of AI embedding system. Why? Because then it would run over time, changing the state of the SUT, learning and running different type of test scenarios that are very complex, and then it helps the operator even to build trust and confidence in AI systems. What are we saying? We are saying that traditional test systems are not suitable for testing intelligent systems. So we need intelligent test systems to test intelligent systems. That's what we are saying. And we had to come up with this architecture called autonomic test system, which is really a closed loop intelligence. Because the question is, if a certain decision made by an AI, can you pass as a verdict? Has it failed? The question of verdicts passing is very tricky. Sometimes you have to learn over time in order to qualify that the SUT's decision it made was correct or was good, right? Based on the trade-off or a utility function that you are evaluating.
Exactly. And here also what you see, I mean, this SUT, of course, this is the complex, let's say, Fabergé egg here in the center. Key enablers are that we had to come up with different roles. So meaning that how to break down testing to enable behavior into different roles, which are including, let's say, a requirement specifier, executor, planner. So all the roles, they had to be come up with from our side in order to really fit into this, let's say, behavior steering of all this SUT. And that's why you see all these actors here and inside, and also orchestrating the different steps or stages of this thing. And that's what is the current outcome.
Yeah, and just to add, in the telecom domain, performance testing of very complex, let's say, systems that we have built over the time in telecommunications, especially switching systems and going beyond switching systems, we find that the performance testing, when it comes to the era of AI-driven systems, takes a more central role than functional testing. So functional testing versus performance testing, we see performance will vary a lot of load and will have to run a lot of tests over time, over months, and has to be able to selectively, thanks to the intelligence of AI, choose what combination of test cases to execute over the time, over the SUT or network under test.
Yeah, and you always need both. I mean, conformance testing is that whether you comply, you test to see if you comply. That's maybe on a smaller scale. But then the performance is that can you scale and still have the performance you need? So you always need both in special operator networks. And the optimal combination is facilitated, let's say, by such systems because you cannot run it linearly or manually through, let's say, regular resources. That's the value of this thing. And,
yeah, so here I talked about the trust and confidence building for autonomous networks. This is the hype that you are hearing with those that are working in telecoms networks and also IP networks. We're talking about autonomic, autonomous networks, ANs. You hear a lot today about ANs everywhere, right? We've been successful with self-organizing networks for the RAN, and we are moving, if you look at the Open RAN, we're also having frameworks like so-called RICs and XAPs and the like. And now, there are two dimensions when it comes to the autonomics. On the left-hand side, you see the 3GPP management architecture mapped with the GANA framework, meaning that you have fast control loops, decisions that can happen in the network element, or even an E not B, for example, and then we have the knowledge plane level decisions. So on that part, you look at the dimension vertically in terms of, let's say, coordination between higher layer autonomics or control loops and the fast control loops. So the trust and confidence building, there are mechanisms to think about trust and confidence building when you have the interworking of the faster control loops in the infrastructure and the slow control loops overlaid on top. So how do you build trust and confidence? Which one is activated first, maybe in the testing and using testing in order to build then the trust and confidence? So the first dimension is the vertical interaction between the two layers. Then the next dimension that you see on the right-hand side is that you have two domains, what we call two domains of ANs, which federate with each other. You could have a knowledge plane for the radio on the left-hand side, a knowledge plane for the core network, and they are federating thanks to this federation broker in between. But it could be across two administrative domains, as we said. One operator on the left-hand side and the other one, and then they are exchanging decisions through the federations. And for this, again, we need mechanisms to build trust and confidence building. One of the mechanisms we have been doing with SON was to operate in so-called open loop, where the SON is making recommendations. It doesn't execute the decisions, but then it has human in the loop. And over time, when the human is trusting more and more, then he tells the SON to say, now operate in closed loop. So those are some of the mechanisms. But what we realize that with AI today for the network, growing the role of the AI, inbuilt AI, we need testing in order to test these two dimensions of federations and interworking of control loops. So there's a framework we are working on that.
Yeah. Here we have a third use case, which is AI-based certification. So we mentioned also the word marketplace. So what does this mean? You can see here in the bottom, what we call AI support system. You have here different, let's say, CSP production environment, for example, training test environment. You have different, let's say, stages or scopes of different stakeholders. And each of these stakeholders has actors inside. And you have different, let's say, sequential stages like procuring, training and testing, deploying, and all the cycle going all the way here. And then you have independent certification of cognitive, let's say, decision elements, third-party testing entities, and you have also the regulatory aspect. You have regulators always that give you directives, what are the ethical, the legal, even sometimes the technical or the data-driven parts that you should comply with. So the concept of, let's say, marketplace is about having, let's say, in each, of course you have here in this cycle, you're undergoing in these stages what we call online learning and continuous learning. The cycle loops back in there. But the idea is that every time you do an AI activity, let's say to access some data, to process data collectively with another piece, we use certification. You also see it later in the last use case as well. Certification is the, let's say, most efficient means of validation that can scale. It allows you to have a trusted way to really trust transactions, trust pieces of data that you share, and to trust a certain function or operation. So certification is a way to really label every action or asset that you are doing. And these different roles in different cycles, they can then, in a, let's say, secure environment, seamlessly, fluently operate on this base. And that's why we call this AI support system, because AI itself has all its stages with certified assets and transactions. And that's why it can smoothly operate. We have also standards that, let's say, reflect this marketplace aspect. You can see the standard here. And of course, one of the key things, as I just mentioned, is that it's a role-based stakeholder model. So in classical, let's say, value chains, you have the old-fashioned, let's say, stakeholders like operator, vendor, integrator, and let's say customer. But today you have disaggregation, you have users using multiple operators, operators with multiple vendors, there's no lock-in. So the ecosystem has become more complex, and we need to go a level down to have within each stakeholder, in the classical sense, to have roles. So within a stakeholder, which is a CSP, an operator, you have roles for test suite owner, certifier, etc. So the role-based model, which we provide in different stages here, and also in previous slides, it's one level below of, let's say, complexity, deeper than the stakeholder itself, if you see it as a bubble. And that's why with this concept, when this thing is operational, you have a marketplace where you can certify an asset, request an asset, you can get it for your algorithm, run your AI algorithm, and then implement something. And then, so this cycle, you constantly need to share data and assets and the transactions to be executed. And if they're all certified, it works like a marketplace. You can solicit or expose assets. You can discover them, request them, and share them. Certification is, let's say, the built-in mechanism. And you can run smoothly your operations here. This is the key idea behind this use case. Yeah, exactly. So this, let's say very quickly, maybe Rang and I could go
I think one aspect, just to give you, will not present this. What we're saying is that test beds need to be federated. That's another dimension that is coming on the market to federate test beds for testing complex systems. And there is work that has been done in ITU.
Okay, great.
Next slide.
Yeah, for the sake of time, we'll cover.
For the sake of time, you can look at
cover the very last use case and wrap up. Yeah. So Telco Data Space and data sharing has been a catalyst. We've been running already twice in TM Forum. It's about, let's say, multi-operator domains, and it's about how do you establish through AI trust among stakeholders to share data among each other. This is, let's say, simplified diagram with multiple operators, Orange, another ISV, Vodafone. There is an app store and container-based services. But I will maybe, for the last minute and a half, maybe share better this slide to show you what we do here. So what we did in data sharing space and how we used AI there, we built what we call an ecosystem consortium governance. So how do you govern your ecosystem, the behavior of your individual stakeholders? Under this ecosystem, over it, there is, let's say, the regional directive of the standards, like, for example, GAIA-X. Below it, we have the governance of each use case. Let's say we have a use case called Trusted AI model. There's a governance box for it, which is this. It governs the behavior. And then there is here the Telco Data Space catalog of services, like a federated catalog of services. This governing entity governs the behavior of how this service container behaves. It goes down further to the individual entities that run the data policy, and then it reports back, just like in the GANA framework upwards, feedback about the, let's say, compliance, satisfying the requirements, complying with the KPIs, etc. So, and we call it SLA monitoring, but it's also in bigger context. So this same idea we applied here, and with AI, and the trusted space, which is, let's say, partially AI steered, we call it data space infrastructure, which is the model where stakeholders can enter the system and then achieve some degree of, let's say, trust, and then share data and run data-driven services. And finally, to wrap up very quickly, we want to say that AI and ML, we took a look from the ecosystem perspective, from the value chain perspective, business impact, and also the outlook. And we said that we have data, let's say, knowledge-driven networking through GANA. We're enabling microservices and behavioral shaping, which is, let's say, AI steered. We showed federated testbeds and assets and new use cases. We talked about telco data sharing in multi-CSP scenarios, and that ecosystems themselves are being, let's say, renewed and extended. And federated autonomics, let's say, which is at its core with AI, a key enabler for this. And the AI and ML will still play a role in cognition continuously, behavioral shaping, which we also envision in our use cases, and automation to leverage those capabilities. And I think with that, we have covered our slides. Thank you. And yeah, hopefully we were on time or slightly delayed.
Exactly.
Thank you. I'm so sorry.